Okay, in this video I want to talk about the linear model. The linear regression model, is the core material for the first half or so of the course, and it's where much of the models that we're going to discuss, also the deviations from it, are really going to be based on. So the course starts out, and any econometrics textbooks tends to start out with first a discussion of linear regression, its underlying assumptions, how it is calculated, and then what happens when you deviate from those assumptions. And so we will do the same. But to start off with, we need to get a little bit of the terminology right, straight, and have a clear specification what I mean by the linear model. And that is what this relatively short video will be about. So on this slide you can see an overview of the terminology that you will see throughout the slide. And I think from the previous course, Quant 1, you will be pretty familiar with this terminology, but I just want to make really sure we're on the same page. So we will often use the symbol y for the dependent variable, the variable that we are trying to explain, the variable that we are predicting. In green it will often be called the regressant. Yeah? So some articles talk about the regressant and regressors, where the dependent variable is the regressant. In political science we really tend to use the terminology of dependent variable. Another appropriate term would be outcome variable. In linear regression, dependent variable is a perfectly appropriate term. In some more complex models that are endogenous, where multiple variables are dependent in a mutual fashion, the terminology gets a little bit confused, but it's not so important. When we refer to X, we refer to the independent variables, the set of explanatory variables that explain the dependent variable. Yeah, so we can call them regressors, we can call them predictors, sometimes they're called factors, carriers, or X as a whole, as a matrix, is sometimes called the design matrix. These are all different terms. In general, I will be talking about independent variables. And in labs or in assignments, I often use a phrase regressed on. I always phrase that as the dependent variable is regressed on the independent variables, just so we get clear on terminology. So the error term or disturbance I will typically be referring to with the Greek letter epsilon. So it is fairly common in statistics books to use Greek letters for population parameters. So these are the actual values out in the population, and then Latin alphabet for estimated or model parameters. So epsilon refers to the actual difference in nature between the values on the dependent variable and the predicted values on the dependent variable based on X and the regression coefficients beta. So we have looked, when we did the lab on algebra, when we practiced with multiplying matrices, we already looked at y minus x times beta hat. Now, x times beta is this linear prediction based on x and based on the values of beta. And the difference between y, so the dependent variable, and those linear predictions, that is what we call the error term or the disturbances. And a lot of the assumptions we make in modeling are assumptions about this error term. So it's very important to think carefully about what the error means. The error is not the difference after you run the regression between your predictions and the dependent variable. It is a difference between the linear relationship given the true regression parameters beta and the independent variables x and the true y. So it is out in nature. It's what is out there. It's not what we necessarily observe or estimate. And this is then contrasted with the residual. The residual is, which we then often denote with an e instead of with epsilon, is the difference between y and x times the estimated values of beta. So if we assume that we measure x and y correctly, and we then estimate the values of beta using some regression model, we can then use these estimated values of beta to calculate predicted values of y, which you call y hat, which is x times beta, and then the difference between the observed values of y and these predicted values of y given our estimated beta, that is the residual. So the residual, if you were to draw a line, a regression line, you have a set of points and you draw a regression line to them. The difference between those points and the line, that is the residual. Because the line is based on your estimated parameters. But if we look at the full data, imagine we had data without any measurement error on the entire population and we could measure perfectly x and y, then we can also perfectly estimate beta, and then we would be able to assess the errors. But that almost never happens. So errors, disturbances are out in nature. Residuals are the differences in our data set based on our estimated model between the observed value and the predicted value. So on this next slide then we specify the linear model, and even though it's a very short slide, this actually is a full specification of the model. In fact, just the second and the third equation of those four is what the linear model is, and it's a full specification. But it's the first equation that probably looks a bit more familiar from earlier references you might have seen to linear regression. So we have an observation on the dependent variable y, say the ith observation. We have an intercept here called beta 0, and then beta 1 times x1 is, so beta 1 is the slope coefficient for the first variable, x is the value on the first variable, beta 2 is the slope coefficient on the second variable, x2 is the second variable, and so forth. I actually note that subscripts are missing here. It should be x1i and x2i. So we have an intercept, beta 0, we have slopes, beta 1 and beta 2, and we have an error term at the end. This is the model specification. So in the model, which is about nature, about what we think is happening that we later then estimate, we have epsilon for the error term. To write the exact same equation much quicker and more concisely, we have the second equation, which is the same thing, but the subscript I disappears because this is for all observations at once. In matrix algebra, we can say y equals x times beta, which is a linear prediction, plus epsilon. And y is a vector of n rows and one column. Epsilon is similarly a vector of n rows and one column. X is n by k and beta is k by 1. So if you multiply those two, you end up with also an n by 1 matrix, and therefore we can add them up. The third equation here shows that we assume the epsilon term to be stochastic. That means that it has a probability distribution. It varies between observations. And this variation we model by assuming a particular distribution, the normal distribution. And I hope you're familiar with the normal distribution, but in a separate video I will also talk a little bit about this distribution. The normal distribution is what is often referred to as the bell curve, so you will be familiar with the shape of it. And in this case we assume that this bell curve, this distribution of the errors in the regression model, is a normal distribution where the mean is 0, the expected value is 0, so this distribution centers around 0, and the variance of this distribution is sigma squared. And sigma is one of the further parameters to estimate. So it is a normal distribution centered on 0, and we have to estimate how much it varies. Another way of writing both equations 2 and 3 is this third one, which is saying, fourth one is saying y is a vector with a normal distribution centered on x times beta and the variance of sigma squared. Now, it is important to distinguish two separate components in this model. So we can think of y having a normal distribution around some mean, we can call mu, and some variance we call sigma squared. And this is the part that is stochastic, that is random, that will vary between observations. Not only will it happens to vary, but we assume that it varies. Whereas this mu part is the systematic part, is x times beta, and this is, we assume, fixed. So we assume that we have certain values on x, and we estimate certain parameters beta, and this x times beta would be assumed to be a sort of a fixed value. Just a side note, this is one of the core parts of frequentist modeling versus Bayesian modeling. So a Bayesian modeler would not make the same argument. A Bayesian argument would be that also beta is stochastic, so the whole story becomes different. But in a frequentist framework, this makes sense. And when we talk about the linear model, we talk about y having a normal distribution around mu with sigma squared. When we are thinking about more generalized linear models, which we come to later, that are not necessarily linear, then we just say that y has some probability distribution f, without specifying that it's normal, around some systematic component part mu and some other parameters alpha, and that this mu is some function of x and beta, not necessarily the linear prediction that you see above. So we have two different parts of the model. We have a stochastic part, the error term, and we have a systematic part, the linear prediction. And so the way to think about these terms is that the stochastic part varies over repeated observations also on the same unit, if you imagine that you would repeat those. Whereas the systematic component differs between observations because the values on x will be different. But given a particular value of x, it should be fixed. Yeah, so if we have the same values on x and the same values on beta, and we make different observations, we still expect to see somewhat different values on y because of the stochastic component. But if x is fixed and beta is fixed and we draw multiple observations, we should always expect the same mu, the same systematic component. And this also leads to two kinds of uncertainty when we make estimates, and this is probably a very important slide here to keep really in mind. We have two types of uncertainty related to these two types of stochasticity. The first is that we do not know these model parameters. We do not know alpha or beta, or in the linear model we don't know sigma squared and beta. And so we need to estimate those. And because these are estimates, we are uncertain about these findings. So we will find a particular value for beta, that is our estimate, and a particular value for sigma squared, that is our estimate. But because we can't observe the true parameters, but they are estimates, there is always uncertainty associated with them. And one specific feature of this uncertainty is that if we had a larger sample, more observations in the same context, we would have less uncertainty. The bigger our sample, the lower our uncertainty in estimating parameters. And as I said, if you have a full data set, you in theory can fully observe these parameters. But there is also fundamental uncertainty that is not part of this estimation, but it's just part of nature. And so even if you have perfect estimates of beta and alpha, you are still not going to know perfectly what the value of y is, because aside from the linear connection to x, there's other factors that are going to influence y. There is uncertainty, variation in the dependent variable outside of this linear relationship with x. Yeah? And so this exists independent of the researcher, and a larger sample is not going to change that. We might get a better estimate for how much it varies, in other words of alpha, but it will still vary. And so we still don't have a perfect prediction of y. So as your sample size increases, your model parameters might be more accurately estimated, but you might still have an equally good or bad prediction of the dependent variable y.